DOS is the original, the denial of service attack. This started off actually when one computer could send a single packet, a malformed packet to another computer and crash that computer. The ping of death, for an example. That is an example of a denial of service. I'm denying service from my computer to another computer or service of a device. From there, it then got into larger and volumetric attacks. And this is where, originally denial of service, if you had a fast enough internet connection and you were faster than the other person, you could overwhelm their connection just from one person to another. If I'm on a 100 megabit connection and you're on a 1 megabit connection, I can absolutely flood your 1 megabit connection. But distributed denial of service attack is going after people with larger internet connections, making use of many different sources of attack, all sending in traffic at the same time. This is usually through resource exhaustion, and we'll go through the different types of resources that gets exhausted from these DDoS attacks. Now, it's not just purely on the technical side of things. There's also the individual and business impact of what is happening with a DDoS attack. A security team is going to see DDoS as, again, that loss of availability, which is a key tenet of the CIA confidentiality, integrity, and availability triangle or triad. From the business side of things, it's going to be impacting the business from a financial perspective. A lot of DDoS attacks are done purposefully to cause financial damage. From here, you look at companies that make money online. So internet service providers, quite obviously, if they can't provide internet service, they're going to lose customers. So that's a common target for DDoS attacks. Credit card gateways, their whole business is processing credit cards. If they can't process credit cards, they don't make money. Online casinos, their whole purpose is making money online. Same thing with online gambling and pay per use for pornography and things like that as well. If their sole or primary way of making money is online and they can't be online, they lose money. The large companies calculate this down to thousands of dollars lost for every second that their service is not available. And if you imagine how long it takes to identify an outage and then troubleshoot and then bring it back up, those thousands of dollars every second that are going away from the business's income and revenue. And you have to think about this. What is the cost per hour of your network or services being unavailable? And this cost can be straight money, money not coming in, but it can also be reputational damage. If your service is constantly going down again and again and again, even if people can stay with you as a customer, they may want to leave because it just doesn't look good. Now, DOS and DDoS attacks can be done through different ways of traffic, and I talked about resource exhaustion. So we've got three main types of attack that we can look at for DOS attacks. This is DOS in general here. The first one is bandwidth exhaustion. I talked about 100 megabit to 1 megabit or traditional for DDoS. You just send so much traffic that you're overwhelming the raw bandwidth of the network connections. And this is where we go back to the analogy that the internet is a series of pipes. You overwhelm the pipes by pushing too much traffic down through it. This traffic can be legitimate traffic. And of course, it can be unwanted, illegitimate, just junk traffic. It doesn't really matter as long as you're filling up the network pipes along the way. And of course, when you fill up the network pipes along the way, you're going to be causing damage along the way. If I'm targeting one customer of an internet service provider and I send enough traffic to that one customer, the whole internet provider may feel the damage of that DDoS attack. The next grouping, rough grouping here, is connection exhaustion. Here, we're not worried so much about the bandwidth, we're worried about the devices that are actually processing the connections. Very simply, if you're doing a connection exhaustion attack against a web server, you're trying to exhaust the concurrent connections that the web server can serve. Believe it or not, they're actually much smaller than you think that an individual web server, how many actual concurrent sessions there can be. Concurrent is sometimes a tricky concept with a website because when you load a web page, you do one request for the HTML and then separate requests for the images. And once that's done, the person is reading the web page, but there's no longer that active connection. It gets timed out and closed off. So just because 1,000 people can read web pages at the same time doesn't mean it's 1,000 concurrent connections because they're all making connections at different times. The 1,000 people reading a web page at one time may only be 100 concurrent connections. And overwhelming 100 concurrent connections is actually pretty simple with a DDoS attack. Now, I talk about a web server because that's usually like the end service. But along the way, a connection exhaustion attack can exhaust connection processing of network devices along the way. If they are meant to only be able to keep state of so many connections at a time, you can overwhelm that. And the network device is then the choke point that gets the denial of service against it, and then anything behind that network device as well. And of course, targeted exploitation. DOS as a denial of service is not purely bandwidth exhaustion. This is what we think about. This is what's in the news. But if you can exploit a vulnerability causing the application to crash again and again and again, all you have to do is keep sending that exploit and the service crashes, and it's a denial of service. It's not some big fancy bandwidth that's not going to show up on any network graphs because it's small little packets, just enough to crash the service again and again and again. Targeted exploitation, really horrible from the network point of view. Now, one thing that we can look at is we can go through by different layers. We can look at the protocols and just the rough ideas of attacks. For those of you that go OSI, here you are. If you want to stay later, you can hear me rant about why OSI isn't what the internet runs on. So I prefer the TCP/IP model myself. They do map straight across. Having a look at the bottom one. So here we're looking at physical data link network access layer. This is where Wi-Fi, Ethernet, fiber, and copper is operating. Here, Wi-Fi DOF. You can do so many attacks against Wi-Fi causing denial of service. You don't have to break into the encryption or anything like that. You can just deauthorize people off of the network again and again and again, and they're not on the Wi-Fi anymore. You can even go old school. I studied electronics engineering. We did a lot of communications classes in that as well. Simple jamming, a simple radio frequency circuit that can just flood the 2.4 and 5 gig ranges and cause every device that operates on those frequencies to just not work because you're overwhelming. You're pumping out more power and you're not letting the others talk. Electrical interference, this is a common one if you've done cabling runs. You've got unshielded twisted pair and you have shielded twisted pair. Why do we run shielded cabling? To prevent interference, specifically in the ceilings with fluorescent lights. Very common one for electrical interference for copper connections. And of course, construction equipment. Who here has heard about a backhoe or a digger that has gone through fiber optic cables? That is a denial of service at the lowest level of the networking. So much so that we used to have a joke at a previous company that the digger machines were magnets to fiber optic because you'd put one in a field and you'd dig and it would catch the one point in the field where the fiber optic was. There was even a news story, this is going back almost 30 years now, a news story of a digger that was on not being used. It was on a truck on a flatbed being moved from one location to another, but the arm was a little bit higher than it should have been. And there was a fiber optic strung between poles and it ripped the fiber optic out of the sky. So yeah, so it's not just digging fiber optic underground. Construction equipment will find fiber optic no matter where it is, and it will cut that fiber optic cable. And that's hard. This type of dealing with denial of service is very difficult. You start getting to the point where a building that needs redundant connections, not only do you have to have redundant fiber optic connections, but you have to have redundant termination points into the building so that if something happens on one side of the building, it doesn't take out all of your incoming copper and fiber connections. Really, really annoying things to deal with. At the networking layer, here we're dealing with IP, ICMP, RIP, if you still use RIP for your routing. A lot of interesting things going on here. Here we can do ICMP floods, and if we want to go back to when I was first starting out my IT career 30 years ago, was the Smurf attack. The Smurf attack used ICMP to go after routers that were on their broadcast address to do an amplification of ICMP traffic. We're going back a long way. If you haven't heard of the Smurf attack, that's an interesting one there. There's not a lot happening at ICMP though. SYN floods, we're dealing with the actual TCP and UDP, not the protocols that use TCP and UDP, but TCP and UDP itself. UDP, there's not much going on there, but TCP has SYN flags, and therefore you can do SYN floods. Doesn't matter what the protocol is above it. SYN flood is, the three-way handshake, SYN, SYN-ACK, ACK. What a lot of people don't see is that you can break it down that it's actually SYN, ACK, and at the same time SYN and ACK the other way. So what we're doing is we're taking the first SYN and the ACK coming back, and we're not sending that last ACK afterwards. SYN flood is a connection exhaustion attempt. Not so much for a web server from a previous example, but the operating system. The TCP/IP networking stack of the server that's running the service can be impacted by SYN flood, which is, of course, part of the problem of the actual protocol design of TCP. But we're probably not getting rid of TCP anytime soon, so we have to deal with it. Then at the higher level, the application, this is where things get interesting. Limited numbers of things here. This is like an unlimited number of protocols. I just put in what I could for the size of a box. And for each one of these protocols, there's these weird and wonderful vulnerabilities and attacks that have taken place over time. Obviously, for ones that are using UDP, there can be reflection and amplification attacks, and I'm going to detail that out with little animations as well. But we also have interesting ones like slow LoRa's and even complex database queries. Here's an interesting one. Think of a very simple web application that runs with a database behind it. If the application isn't written properly, what someone can do is send in a complex search query that makes the database have to do a lot of work in order to spit back the results. If you keep hitting the web server with these different queries that can't be cached by the database itself, you're going to make the database churn and go again and again and really, really work hard. And if it's not optimized and if it's not filtered, you're going to then cause the database to be the denial of service target. Things like slow LoRa's and similar ones were interesting. The connection exhaustion is where similar types of attacks. They would make a connection to the server. Sometimes this is an SMTP server, carried from a previous talk. And they would make a connection, and they would figure out what is the slowest speed that you can send information that the connection wouldn't drop. And it might be like every 10 seconds, they'd send one letter. So, mail from, receipt to, mail from, they'd send M, A, I, L, and they would go through the email message so slowly to hang on to that connection. Now, if an email server can only handle 100 concurrent sessions, you just run up 100 threads talking to the server so very slowly that the connections stay open, legitimate connections can't come in, and you've created a denial of service. Really interesting stuff. And this is interesting because most people expect when one server talks to another server, it sends the email as fast as it possibly can. But what happens if we abuse the protocol parameters and do it slowly? Some trends on DDoS attacks. This is not every one of them. This is just sort of a rough gauge of things going back, what are we up to, 13 years or so? They've grown, they've changed. Go back to late 2012, we had a 60 gigabit per second attack. 60 gigabit per second is a lot. You know, at home, I don't have 60 gigabits per second. APNIC and past companies I've worked for don't have 60 gigabits per second just to their one data center or server room. A year later, it was up to, and these were maximums at the time, it grew 5 times to a 300 gigabit attack against Spamhaus, a spam filtering company. We then go a year later, and it's up to 500 gigabits per second. We then go 2 years later against DNS, a dynamic DNS provider that had a lot of people using their DNS servers, 1.2 terabits per second. And what happens when DNS servers are no longer available? Domains don't resolve. The impact from this was huge. A couple years later, hasn't changed too much. There was a 1.3 terabit per second attack against GitHub. Again, large impact because of how big GitHub was. A year later, 1.7 terabits per second. A year later, we're up to 2.3 terabits per second. This was against AWS. And then things get interesting because some attacks weren't going pure volume, but they were more connection-based. So here we go requests per second. So these are more connection-oriented. 17.2 million requests per second sustained. That was crazy. That was an attack against Cloudflare just a few years ago. And you know, to kick things up a notch, 400 million requests per second. That is insane levels of DDoS attack against an organization there. Now, there are reports, many reports that show many things. The one that I like to think is most reasonable is that most DDoS attacks against the average organizations, take out Google, take out GitHub, take out AWS, the average DDoS attacks against average organizations is only between 1 and 25 gigabits per second. And for an organization that may only have 1 to 5 gigabits of bandwidth, yeah, that's going to take you down. And they usually last less than 4 hours. Some of them as short as just a few minutes. And the reasoning for that is a lot of these DDoS attacks are done either to make a small point or, you know, be funny against somebody with a gaming account, or they're for ransom. They do a short attack for 5 minutes, long enough that the business feels the impact. Hey, what's going on with the network? Why is the website down? Why is everything else down? And after that 5-minute DDoS attack, they send an email to the organization and say, hey, did you feel that? That was us. We can do it again. Pay us money, and we won't do it again. There was a very famous one, DD4BC, DDoS for Bitcoin. And their whole thing was they will do a DDoS and request Bitcoin as a ransom. And so much so that in their emails that they would send out as part of ransom, they would link to news articles of past times where they had done a DDoS and made it into the news. And they say, look at all these news reports. We can take you down for a long time. We've done it before. They also said, and it was hilarious, I don't have a screenshot of DD4BC's email, but they say, but we have high integrity. If you pay us, we promise not to come back and attack you again. We've got good integrity as criminals. It's hilarious. I don't think DD4BC exists anymore as a group, but DDoS ransom is a very common one out there. Remember, companies, large companies, can have value down to thousands of dollars per second for a DOS attack. So let's have a look at what do these actually look like. Now, plain, simple DOS attack. This could be exploiting a vulnerability or the 30 years ago sort of thing. So here we have an attacker. They're either going to send valid traffic, and a lot of it, or invalid traffic to cause a crash. And they send traffic to the victim, and the victim catches fire. Figuratively, not literally catching fire. So that's just a DOS attack. One attacker, one victim. Now let's have a look at a simple DDoS attack for the distributed aspect of it. Here, an attacker directs a botnet. So they have a remote control botnet. Some of the good classical ones, the infected software, the viruses that were infected on these machines would join an IRC chat server, and they join a chat room, and they just listen. The attacker joins the chat room and says, attack this style against this IP address. And all of these would hear the chat message and go, then they go off and attack it. Really simple command and control using IRC servers. So one little message to the botnet, and now the botnet sends their traffic. Now this traffic, again, could be valid traffic, a lot of web server requests in order to fill up connection tables, or invalid traffic. But here you have a large number of computers all sending traffic to the victim. Some of the largest botnets that I've seen and operated around were around like 500,000 computers, all under the control of one person or one group. It's a lot of work. Like, think about how many computers exist in your organization. Now think about trying to manage 500,000 computers and keeping them up to date and connected and everything. It was a multi-level job. It wasn't just one person, but there's one person recruiting bots, one person keeping them up to date, is a whole thing. In the end, 500,000 computers is very unmanageable. So that's why you see more botnets of smaller sizes. 10,000 computers, 25, 30,000 computers at a time, which still can cause a lot of damage. So that's just a simple DDoS attack. Here, let's have a look at the more complicated one. So this is reflected and amplified. So we take the same concept of one attacker and a botnet, but we're going to reflect the traffic and amplify it to make it even worse. So again, the attacker sends one command to the botnet, starts off the same way. But here we start to see some other players in the middle of things. Here, if you could just move the maybe down to the bottom left for the, yeah, perfect. Here, what we're introducing is DNS servers. Now, these DNS servers are not your normal, well-secured DNS servers, but these are open recursive servers. So recursive is where users send their request and it goes off and forwards it to somewhere else. Open means that anybody on the internet can use them. Now, this is open for abuse because criminals and botnets can use them as well. So step 2, the bots send DNS queries for a text record. Here we're using evil.com. It's just a made-up domain. It's not the actual evil.com. And they send these requests to these DNS servers, spoofing their from address. Because remember, this is UDP. There's no three-way handshake. We can spoof requests, and it's great and wonderful for criminals. So here, they send their requests to the open recursive DNS servers. Now, they're recursive. They're not authoritative. So they don't know what the text record is. They have to go out to the authoritative name servers. So introducing the authoritative name server. This is run by the criminal so that they can have their domain and they can configure the text record. Now, TXT text records can be quite large. I think on the record here, it's around like 4,000 bytes. So you can fit a lot of information into a text record. So here we have the authoritative server that has the zone file, that has a TXT record, 4,000 bytes long. The open recursive DNS servers query here once in order to get it, and then they cache the response. So here they send a small request, what is the text record? And the reply is quite large. The reply is 4,000 bytes long, so it's one big chunky reply. But once this is done, the recursive DNS servers cache it, and they don't have to talk to authoritative anymore. Now remember, the botnet spoofed the from address, right? So here we have, you can throw it back up to the top right, thank you. Here we have the victim. The victim has the spoofed IP address, so the replies are all going to be sent down here. I tried to make it with small little dashes and really big dashes. The request is really small. What is the TXT record for evil.com? The reply is 4,000 bytes long for every single one of these requests. Now, this is a pool. Imagine 20,000 computers. This is a pool. Imagine 2,000 servers. You've got 20,000 hitting against 2,000 that then is multiplying the size of the traffic. Now, these requests are for DNS. This doesn't have to be listening on DNS. This is just purely receiving UDP packets down a pipe and would overwhelm any reasonable business. This is how you get gigabits and terabits per second of traffic, is a botnet, a reflection, and an amplification. So what makes for good reflection? UDP. You can't reflect TCP, or at least not in a reasonable way. You can reflect off messages, but who cares about ACK messages? UDP is spoofable, forgeable with source IP addresses, and it's connectionless because no three-way handshake. What makes for good amplification is where you're dealing with a protocol that can have a small command or a small request that generates a large reply. This is called the bandwidth amplification factor. You take the reply, divide it by the request. So for example, this is a real number here, 3223 divided by 64. So this is the maximum reply. This is the average or maximum request. And you get an amplification factor of 50 times, which means if you can send 1 megabit per second of request traffic, you get 50 megabits per second of replies out of it. This is a simple chart. This changes, of course, as new protocols are brought out and problems. These are largely all using UDP, which makes it great for this bandwidth amplification, reflection amplification attacks. SNMP, a lot of people don't expose that. It's only a 6.3. RPC bind, hopefully not very accessible on the internet. DNS, common. SSDP, very common as well. These can amplify 30 to 54 times. LDAP, if anybody has a public LDAP server, of course, that can amplify things. You send a small request and you get the full information for an entity. TFTP can do large ones as well. If anybody remembers playing Quake, the Quake gaming protocol had a 64 times amplification. RIP v1 shouldn't be out there, but it's for documentation. Quote of the day, if anybody's on Linux and you know quote of the day, again, it shouldn't be exposed out publicly on. Chargen, character generator, again, shouldn't be exposed on the internet, but character generator, you just make the connection and it just spews out traffic out like text ASCII characters. Hilarious. NTP. NTP with a particular vulnerability. So this is not every NTP server, but there are vulnerable servers out there right now on the public internet where you can send a small request and get a 557 times multiplication of traffic. And that's because the vulnerability is where you send a request and it gives back sort of like a log of entries. So it's a lot of information in that response. So huge amplification factor here. And Memcached. Memcached had a vulnerability in its early days when it was getting a lot of traction, a lot of people using it. People were spinning up test instances and new things, and they would put Memcached on public IP addresses with no ACLs and no filtering whatsoever. And there was a vulnerability, again, not current Memcached. I'm not crapping on Memcached here, but a vulnerable version. And what it allowed for is you to upload a file via UDP and then request the file by UDP. And you can request the file again and again. And we're talking like, say, like a 1 MB file, tiny little request, 1 MB file for each request, huge amplification factors here. 51,000 times. So like if you had a 1 Mbps internet connection and were sending Memcached requests, it would end up being 51 gigabits per second of traffic. Like it's insane. And that's just from one connection sending it through. Just to give you some real stats, DNS can be exploited just normal. So if anybody plays with DNS, you can actually send the any command or the any query. Any will respond a whole list of different things. Depends on the configuration of the DNS server, of course. Here, this is just a screen grab that I did from some very quick Wireshark captures that I was doing. You can see that I'm just doing a DNS query for 88888, and the request was 80 bytes long, and the reply was 372. Very, very simple. Even larger, I did an any query against Microsoft.com, and it was 73 bytes long for the query, 530 bytes long on the reply. Here, you can see the reply back for any Microsoft. It gave the NS record, the start of authority, the MX, text record, text record, text record, text record. And this is a legitimate text record, but look at how long it is. So see how much information that you can pack into these things. Crazy, crazy stuff. So protecting your services from connection exhaustion attempts. If we start at the far end of things and we look at the service that you're running and the operating system of that server, you get down to the TCP/IP stack level. Now, this depends upon the version of the kernel that you're running, any other tuning or tweaking that might be in place, and how that all fits in with things. But you can look at things like TCP/TW reuse on Linux so that you're not dealing with a connection exhaustion as much. Decreasing the TCP timed wait delay. Some of these connections, like at the TCP connection level, will stay half open for like 5 minutes. That's a huge period of time to keep a connection still in memory. So absolutely decreasing that. And of course, enabling SYN cookies. Now, most modern operating systems will enable it. Depending upon what you're doing, you might even want to disable it for certain types of load balancing and stuff that you're doing. But understanding SYN cookies and how that operates so that you're not keeping the connections in memory, that you just do a little bit of math to determine whether your final acknowledgement matches up with the first SYN and ACK messages as well. Also configuring service applications. This is an example that is specific to Apache and Nginx, but this applies to any services and how they're actually processing the application connections, not the TCP connections. Slow Loris was one of the ones where it actually was going after Apache because Apache was using the event-based MPM at the time by default. Nginx was an interesting way because it wasn't using event-based. So what you could even do is put Nginx in front of Apache and it wouldn't be susceptible to the event-based problems that NPM had at the time. So yeah, interesting things, but this is just one example, but all of your services have to be looked at as well for, is my SMTP server configurable to stop certain types of attacks that are going against it at the application layer. Moving back from the service a little bit onto the network, of course, you can implement intrusion prevention systems or DDoS filtering. A lot of the next generation firewalls or, newer, whatever you wish to call them, whatever marketing terms they're using, these have functionality built into a lot of these firewall devices. Some of them may cost money for subscriptions or licensing, but they may be there. Even if your firewall doesn't provide DDoS attack prevention, some IPS systems will prevent certain types of DDoS. Remembering that DDoS is just a type of traffic coming through, and an IPS, if the rules are written correctly, may detect some of that and be able to block some of it. Tricky thing here, though, the traffic is already reaching your firewall at that point in time. So your upstream could be overwhelmed with bandwidth. But if we're talking connection-oriented, yes, absolutely. Put in the protection at the layers that you have available. Another one is, of course, changing the architecture of your systems. If you can only have a web server that can handle 100 connections at a time, like absolute concurrent connections, and you need to handle more load, whether it be real load or abuse load, load balancer, additional servers behind it, re-architecting the solution so that you have more servers dealing with it. Because not every DDoS is bandwidth against the network. Connection-oriented is a very real threat. Web servers. Web servers, of course, have web application firewalls, very similar to like IPS at the network layer, but these actually can inspect inside of encrypted connections. The web application firewall terminates the TLS connection, decrypts it, actually sees what is the request, and can at that point then determine whether it needs to filter or pass it on. Free WAF, there's a few new ones that are being built out there. The old school, classic one is mod security. It can run on its own, it can be, or you can put it on its own box as a reverse proxy in front of a web server if you can't modify the web server itself. Really interesting things. It's freely available. There's a free set of rules. There's also a commercial set of rules. Depending upon, how fast you want the rules released. So these are closer to the end side of things. Here, we're going a little bit further out onto the network, installing a dedicated on-prem DDoS filtering appliance. So this is a box that you'd be putting towards the edge of your network device. Pros here, low latency. You're dealing with usually a physical device. Sometimes ASICs or programmable gate arrays. High degree of control because you can install your TLS keys onto it. It can do the decryption, look at the traffic, make decisions based on that. Of course, these are something that you have to buy. So capital expenditure is quite high up front. Does still have the bandwidth limitations because this is still on your side of the network. And of course, you need some technical expertise in order to, deploy them and tune them in that. Here's some little graphics that we have here. The black lines are normal connections. The red lines are where the attack traffic, where the DDoS traffic is coming through. So here we're dealing with a network, a few routers, 2 upstream connections. The target is the one being attacked. So of course, the traffic comes through the redundant connections, goes through here, and bang out to the target. If we mirror it across, and we put the DDoS appliance just in front of the target, what we're going to deal with, it is still there. What we're going to deal with is still all the traffic coming through the 2 uplinks, going through your internal routers, and then it gets stopped there. The target is relieved, but the network could still be impacted. Now, of course, remember that's more on the bandwidth side. If it's connection-oriented, you may not even notice a blip on your network monitoring graphs. But the connection blocking absolutely make the target now available to legitimate users. So it's not useless. It just has a limited scope of being best against connection-oriented DDoS attacks. Now, protecting your network for bandwidth exhaustion attacks. Starting off up at the top, proactive rate limiting. If you're looking at non-initial fragments, usually it shouldn't happen because window sizing and that should be changing properly. A lot of the traffic is fragments that are appearing to be in the middle of a connection. So yeah, be careful though, if you start doing things like this, that DNS can be weird with fragmented packets later on. So you'd think like, all applications will behave this way. And then you come up with this really old application like DNS, and it's like, oh no, the way it does its packet fragmentations is different. You also may want to look at commonly abused ports and apply rate limiting at the network layer for things right up front as much as possible. You can also do reactive rate limiting. So this is when you detect an attack, you have triggers, you have alerts from your network monitoring, and you can then rate limit traffic from less critical network locations. I've seen many ways of doing this. One common one is having your main uplinks and having a small burn link. And basically, whoever's being attacked, move the traffic from maybe outside of your country off to that burn link for that destination targeted IP address from there. I've seen that in countries where a lot of traffic is domestic, but of course the attack traffic will be from all over the place. So take the international traffic, put it onto your burn link. On the more fancy side of things, remote trigger black holing. Now, do I have? Yes. So remote trigger black holing, here we have our red traffic coming in all the way along, filling up all of our bandwidth, hitting our target. Here we have a triggering router. Off on its side, this is your management, your security router. What it does is actually it sends triggers after it sees the monitoring, sees where the traffic is coming from, what's being attacked. It puts the triggering out to your edge and says, hey, any traffic that was meant for that target, just throw it into the bit bucket. We do not want this, just drop it completely. Your target becomes unavailable because you're sacrificing at this point in time. But you see these lines down here, these are all black. These are no longer red. They're no longer full of bad traffic coming down. So you're sacrificing the one so that the rest of the network can keep going. Sucks for the person who gets, black holed. Now, if you have a good upstream internet provider and they provide the service and you communicate with them and you work on the negotiation on how it operates, you might be able to do remote triggering to your upstream. And if once you do that, now these connections are now traffic free, attack traffic free. Your target is still offline because you're black holing that address for the destination, and the ISP is still dealing with traffic coming in from everywhere. I do have an animation for it. So your ISP is still dealing with all of this botnet traffic coming in, so sucks to be them, but hopefully they have more bandwidth up here than what you have coming down here. So this requires availability of a service and communication and maybe some sort of contract with them for how that operates and how it gets used. And of course, you can install multiple servers. So here you have a target that is on your network, but if you put copies of your, copies of your service, like a web server or whatever, you put them out into other data centers and you spread them geographically, and you're using Anycast. Anycast is using the same IP address everywhere for each one of the servers being run. And because it's using the same IP address, any of the attack traffic is going to go to the closest Anycast location for your service. So for example, the botnets that are here, maybe this is a country or a continent, they will go to the closest one. They can't go down to there because it's Anycast. It goes to the closest point. So here we can see that happening. The traffic's going to here and there, and it's spreading the load. If you do this with big enough servers and providers, this is like the Cloudflare distribution network sort of thing, or any of the others that exist, you're spreading it out so big that the traffic can be managed by each of those POPs. And of course, talking about cloud scrubbing, this is the same thing here. So not only the previous one that we had, the previous one, what we were doing was here, where these targets are still getting DDoS traffic sent to them. Here, when you do a lot of the cloud scrubbing, Imperva, Cloudflare, Akamai, that sort of thing, it goes not to your destination, but it goes to their POP, their DDoS scrubbing appliances and devices that they have, and they filter out the bad traffic and let through the good traffic. The good traffic, of course, represented by the green dots that still can make it to the target. And yeah, it's a constant battle because they're dealing with new types of attacks, always having to update their defenses. allowing the good traffic through as much as possible. A lot of this good traffic through is done over a GRE tunnel as well. So again, it's a little bit more engineering on your part. This is not something that you can spin up during a DDoS attack. This is more having something built, prepared, paying money, and having a contract ready in advance so that when something happens, you can either switch to it or always have your traffic going through these sorts of scrubbing centers. So mitigation strategies. So protecting your service from attacks. We talked about Anycast, talked about intrusion prevention systems and DDoS filtering and overall network architecture. What we have to also remember is the internet is a community. Not only do we have to protect ourselves from attack, we should not be participating in attacking other people. And I'm not saying that you're actively participating, but if you're not configuring your networks and your devices properly, you are passively participating and allowing this type of criminal and illegal activity from happening. So protecting your services and your network from outward attacking other people, rate limit any of your outbound connections. Do source address validation for your outbound filtering with BCP38. This has been around for a long time. This is not new. This is not magic. People should be filtering the IP addresses going out to prevent your network sending spoofed packets. Your network that you control should not be sending any spoofed source address packets out from your network. If you're running services that are publicly accessible, DNS, NTP, SNMP, SMTP, well, not so much because it's not UDP, securely configure them so that they cannot be abused. It's okay to run public NTP, but if you're running a vulnerable version, it's going to be abused and used for attacks. If you're running DNS, don't have any public open resolvers. You need to have resolvers, yes, but limit where the resolvers can be accessed from by your network ACL so that it's only your network that can access your open resolvers. Yeah, there we go. So that is the end for DDoS. It's a quick run through. It's not a magic silver bullet, but it's looking at all the aspects of how things are going and common ways. There's probably a few other ways of doing mitigation techniques, but they're variations on that. There's an interesting one. Sorry. There's a variation on this where we do remote triggering, where like this is you communicating with your upstream, right? Now imagine that you had 1,000 friends around the world that are operating 1,000 large internet networks around the world. If you were being attacked and some of the traffic was coming from these networks that your friends operate at, wouldn't it be cool? Wouldn't it be cool if you could say to your friends all around, 1,000 networks around the world, hey, can all of you guys just black hole this address for me? And then the traffic, a lot of that attack traffic will get stopped much closer to the sources of where it's coming through, causing less impact for everybody on the way through the internet. Team Cymru has something called URTS, URTS. T stands for traffic, but I can't remember the full acronym. It's basically that. It's basically getting a community of network operators together where everybody talks and everybody agrees that if any one person pushes out an announcement to the group for their own IP address, you're not allowed to announce other people's addresses. You can't DDoS other people. But if you announce one of your own addresses, everyone will just do a black hole for it at their edges. And if we get more people involved in that, we can then block more attacks, more traffic closer to the sources of the traffic and relieving it for more people. So really interesting stuff. But like I say, it's a variation on this. But just instead of the ISP, it's your 1,000 closest network engineering friends around the world. Let me just find One second. Where's my mouse? I think it's Ooters, isn't it? Ooters? Oh, where is it? UTRS? I'm probably spelling it wrong. There we go, UTRS. Unwanted traffic removal service. Team Cymru, if you haven't heard of them, and if you operate any sort of networking or security, check them out. They've got a lot of really cool stuff. They do some paid things for some people, but they also release a lot of stuff that is open for the wider community. So this is an interesting one. Have a read of it, utilizing techniques like remote trigger black holes, but globally. Really cool stuff. Beyond that, if you wanted to do assessment of your services for things like open resolvers and NTP and that, if anybody hasn't heard of Shodan before, there we go. So Shodan is basically an organization. There's a few others. Census, CENSYS is another one. What they do is they scan the internet for every port, every protocol, and they listen for the banners and the information coming back from them, even screenshots of web pages and stuff. And they know what services are running on what IP addresses and what the version is of every service that's out there on the internet because they're constantly scanning and building a database. Now, if you're running, say, bind version 123, and right now there's no vulnerability in bind version 123, great. But as soon as a vulnerability is discovered, like there's a vulnerability in it, we just don't know about it right. Yeah. So as soon as a vulnerability is discovered and published, all a criminal needs to do is go to here and say, find me every bind DNS server running version 123. Boom, there's their list. They can exploit the vulnerability to either crash the machines or bounce them off. If you want to find open resolvers, you can do it. You want to find SSDP servers, you can absolutely do it. I'm not sure. So I just did a search for SSDP and yeah, so there's a few of them. Synology server. So yeah, it's interesting stuff. So yeah, so this is open, this is available for you to defend your networks. But one of the best ways to defend your network is to know what is visible. And they've got a database of it. And this is where some criminals will go to see what is visible on your network. So you can put in your IP address, network range, and see everything that's there. You can start going into searching. You can do paid versions of Shodan, and you can do scanning and reporting and graphing and a whole bunch of really cool stuff. But yeah, it's a little bit scary if you haven't seen it before and how powerful it can be. But it's another aspect of things. Know what is on your network. And if you don't have perfect visibility inside your network of all of your services, at least have a view from the public perspective of what is on your network. And if there's anything that really shouldn't be there or should be updated or ACL'd and blocked off. So yeah, so that's another one. And as I said, the other one, it's not just Shodan. I'm not just talking about one organization or anything like that. Census is another one. Shodan recently have put in some more limits on the free access. Census has a little bit more free access, but both of them are very powerful when you're a paid account. Shodan in the past has done Black Friday specials, like $20 for a lifetime of access for personal levels. But yeah, really, really interesting stuff. But you can see what they've been scanning here and what they have access to. So it's crazy stuff. Let's see if anything is still accessible on that old address. So there you can see DNS, and it's an authoritative name server. So that's the type of scanning. They're not just checking if a port is open, but they're speaking the protocols to see what's going on. Over at Shodan, I know there was one here where you could even search up webcams as well. I'm sure there's a better search than literally typing in webcam. But yeah, you can do that. And no, that's the point where you have to log into it. But yeah. It's saved my password. Let me see. There, yeah. So I just literally searched for the word webcam. I am not doing a complicated search query here, okay? And these are publicly accessible webcams with the latest picture when Shodan did a scan. How cool is that? I'm glad there's nothing. No, there's nothing that I shouldn't be putting up publicly there. Good. Yes, I'm sure there is. Like some of these might be people that are doing it on purpose, but some of these might be people that don't know that their webcam is publicly accessible and could be pointed in their children's bedrooms. Not cool, not cool. But again, know what's out there and see what there is. So like here, this is back to webcam. And again, I'm not saying that these are all malicious or accidental or whatever, but you can break it down by country, you can break it down by ports, by network organizations. It's really, really cool, powerful stuff. Yeah.
I'm just curious, in the map that's displayed,
Yeah.
most countries are displayed red. There's some section of Africa which is just white.
Yes.
Is that a reason for it?
Possibly not there. But yeah, it's basically for the query I did, it's not returning there. So what you could relatively safely say is that people in Central Africa and Northern Africa don't have publicly accessible webcams.
And I saw similar trend in the previous search as well in SSDP.
Yeah. Less networking stuff.
Okay.
So this one, let me refresh. I think this was the SSDP. Again, visible, publicly accessible SSDP is not a good thing.
Yeah.
So it's actually good that Africa doesn't have a lot of them. Now, it could be a whole range of factors, either less internet connected devices or better security. Yeah, you could look at it from many different angles, but all it's simply saying is where these hosts are coming from are the ones highlighted in pink through up to red. So yeah. And then we can narrow it down, click on Hong Kong. And then, all of these hosts are now Hong Kong and you can see everything. You can even search by TLS and SSL certificate information, which is really cool. So yeah. So know what's out there and do prevention from that aspect as well. Does anyone have any questions either online? No questions online? Any? Yes.
Basically, we didn't discuss about the automated systems. So firstly, there are like two aspects to it. Firstly, automated systems can be used by the cyber criminals to
Yep.
carry out the DDoS attacks.
Yes.
So how to mitigate that firstly? And secondly, if there's like an IoT device, for example, which is running based on the automated decisions. So if a DDoS is done on that particular IoT device, so how can we mitigate?
Yeah, so question for people remote, question was around attackers using automated tools, as well as the IoT device side of things. The attackers using the automated tools, the best thing is then automated defenses. And I'm trying not to promote any one company or vendor or things. And unfortunately, if you want top tier protection, you're going to be paying top tier money. If you put all of your traffic through cloud DDoS scrubbing services, it's their job to deal with all the attacks, whether they be new attacks or modifications or anything like that. But some organizations, they don't switch to DDoS scrubbing centers all the time their traffic is going through. And this is a common one with Cloudflare. For example, let me just bring up a very, very simple one here. And again, I used to work for APNIC, so this is a very easy one. You know, NSLOOKUP www.apnic.net goes to a CNAME of www.apnic.net.cdn.cloudflare.net. When you visit the APNIC website, you are connecting to a Cloudflare server. And then behind the scenes, the Cloudflare server is connecting to the authoritative web server for APNIC. This is all the time. This is every single request. And of course, it's a CDN, so it's a content delivery network. So they do caching, they do all sorts of fancy stuff, as well as all the WAF and DDoS scrubbing stuff as well. So yeah, automated attacks, automated defenses. This sort of remote triggering black hole from previous slide. This sort of remote triggering black hole. Like, yeah, of course, you can manually log into a router and send a BGP message out to your edge or up to your ISP, but this can be automated as well. This can be watching a traffic coming in, hitting certain thresholds, determining what the target is, send the triggering up to it, as well as then sending an alert to the NOC or SOC or anything like that. IoT devices, I'm not a huge expert on IoT. There's a lot of things that you can do in there. I will give you one very sideways interesting bit for IoT devices. Imagine you have a smart TV at home. You buy your smart TV, any brand smart TV. You might get software updates for the first year, and then it stops. But you still keep using your TV, right? And it's internet connected, right? So it's IoT. It's online, you're interacting with it, but you're not getting software updates, which means vulnerabilities aren't being fixed. If somehow malicious activity gets into your network, starts scanning and starts infecting devices, it'll find your smart TV, IoT device with the vulnerability, and it'll try and put malware onto it, right? The malware then turns your IoT into a remote-controlled bot to join botnets and everything. Command and control for botnets uses DNS. So here's a really interesting thing. There are DNS filters out there. They use RPZ, response policy zones, to do DNS filtering. There are public ones that you can use without even paying money or signing up or anything, where you can use that at home. If you change your home router's DNS to not use your ISP, but to use a filtering one that filters malicious domains, malicious activity gets into your network, infects your smart TV. Your smart TV tries to do a DNS lookup to join the command and control. The DNS lookup fails because it's a malicious domain and it gets blocked. Your smart TV is infected, but it's not doing anything. Huh? There you go. IoT, of course, network segmentation at homes and off IoT devices off on their own so that they can't crosstalk and everything. But I am a really big fan of DNS filtering. I love it so much. There are so many uses at home as well as in the workplace as well. Not just filtering to block gambling for people in the office, but to block malicious domains and security. A lot of the commercial DNS filtering also blocks or has an option to block newly registered domains. Now, there's false positive hits on that. Someone sets something up and it's not working because it's being filtered. But it also means as criminals are starting to set up new domains and trying to do phishing or other attacks, if it's a newly registered domain, 30 days is what they usually are, it's going to fail. Someone gets a phishing email, they try and click on it, the DNS doesn't resolve, so they can't go to the phishing website. Huge fan of DNS filtering. I use a small home one, small bit of money, like $2 or $3 US per month. I set up profiles for my children so I can block applications, not just blocking malicious domains and things. I can block them from accessing TikTok. I tick a button, tick a little box, and every TikTok domain now gets filtered off from my children's profile, and their DNS is then configured on all their devices. So even if they take their device and use 5G mobile connections, they go to their friends' homes or anything like that. As long as their device is using that DNS filtering service, everything's locked and protected. I love it. I love it. I love it. But there are many ones available. If you want to use the one that is absolutely free, because I'm not going to promote other services, it is called Quad 9. And it's as simple as, well, quad9.net is the website. Change your home router to use DNS 9.9.9.9. You know, Google's it's 8888, Cloudflare 1111, 9999, free, and blocks only malicious domains. So it's not going to block pornography. It's not going to block gambling or other things like that. Only malicious domains. So like the easiest thing that will have like zero negative impact or almost zero negative impact, Quad 9. So there you go. And you can run your own within a organization, within a business or research education networks and stuff. You can run your own server and bring in your own threat intelligence feeds and do your own thing so that if you're getting some false positives, you can go through and tune it and tweak it and bring in your own information. Yeah, really interesting stuff. The European Union is running one. DNS EU, I think it's called. Taiwan? I think Taiwan is running one as well for their country, for their economy. So yeah, really, really interesting stuff. So yeah, bit of a side note. Not exactly DDoS. It's a bit of DDoS because it can stop botnets, you know, for infected machines. But yeah, really, really great stuff. And like very small number of internet providers do any DNS filtering. So like the average home user using their ISP's DNS, they could join a botnet, not know it, and everything would be horrible. So, did you have a question? Oh, okay.
They asked one.
Explaining about simple DDoS attacks, I had a very curious question that in the botnets, they said that the attackers use around 500,000 computers.
Oh, yeah. Okay. So the question's about the size of botnets.
Or like virtual PCs or like
It could-
how an attacker manages 500,000?
So the question's around when I was talking about simple botnets and that, and how there were large large botnets. So all the way back here, where we had the botnet here. So yes, the largest was 500,000. At the time, virtualization, this is going back many years, 20 years. At the time, virtualization wasn't a popular thing. So yes, that would have been 500,000 individual operating systems, probably on bare metal, some of them servers and some of them home computers. And that, at 20 years ago, was the big thing, that home computers, of course, had smaller internet connections. You get enough computers and you would get a lot of traffic. But if you could get servers into your botnet and the servers have fast internet connections, ooh, think of all the things you could do. But yes, managing 500,000 infected computers was horrible because you also had other criminals that were setting up their own botnets, and you would actually have some criminals that would be like infecting already infected computers and getting rid of other botnet software, other remote control software, putting their own in, and they would be fighting over these infected computers as resources. So some of them would actually delete and remove other infections and put up some protection so that it doesn't get reinfected by other pieces. So yeah, it was a huge thing, still is, because vulnerable machines are a limited resource, and you want to control as many as you can, and have them spread around the world so that you can attack from many different angles. So yeah, but yeah.
Fight against the victim as a fight against the attacker.
Exactly, yeah. And a lot of these criminal groups, they are a layered organization. A lot of crime is different people doing just their one piece of the puzzle. Like for something like this, there'd be one person just writing the software or updating the software, personalizing it to do the control. One person handling the command and control servers. Nothing to do with the bots or the infections or the attacks, but they're running servers for that command and control communication and securely without it being taken down or intercepted. Some people that would be infecting the computers, making sure they're up to date. Some people purposefully trying to kick out other botnets, and then the people actually issuing the attacks. The ones issuing the attacks are like at the higher level, and they've got all these lower level people that are keeping the infrastructure up and running. You look at things like phishing, Viagra scams, for example. You've got people that are writing the emails. You've got people that are sending the emails. You've got people that are filling the orders for fake pills. And the money flows through. Everybody gets a piece of the pie as it goes through. So it's a huge underground economy of financial crimes behind all of these things. Yeah, scary stuff.
With user and questions, not much.
Yeah, sure,
Are you
sure.
sure that some people can actually try to see the security camera live publicly available?
Yeah, yeah.
How can I know like my home camera is not publicly available?
Yeah,
How
so
can I stop it?
question was around seeing the public webcams. What can you do from home? The same thing that you can do in an organization as well. If you know your IP address or IP address ranges, you take your IP address, put it into a search site like Shodan or Census, and see what it sees for your IP address. Now, of course, if you ever want to see what your IP address is, it's just as simple as like, what is my IP? And that shows you what your public IP address is, right? So what is my IP goes out to Google. Oh, actually, yeah, it's not returning it right away. So let's go to this website. What is my IP address.com? So what's happening is my computer is talking to this web server. And even if we're using NAT here, what the web server sees is the public IP address, right? And all it's doing is echoing it back to me. It's like, hey, I see that you're coming from this public IP address. 223.197.32.148 Hong Kong. So there we go. So that's my public IP address. So I can take that address for like a home network, throw it into Shodan and see if anything is being seen from the outside. And then of course, if you work for an organization, you should know what your network ranges are, /24s, 20s, 18s, 16s, whatever. And you can do a search in Shodan for the entire thing. Ooh, and I've been not plugged in for power. So you can search your entire network and get the report back on all the open services. Of course, some open services will be normal, DNS servers, email SMTP servers, but you want to look for anything that is abnormal or version numbers that you're not expecting. So yeah. Yes, okay. Yes.
So at Aura, I work with a lot of DNS abuse,
Yeah.
and what I see is the main targets are small businesses.
Yeah.
So what would your suggestion be for small businesses which might not have enough resources to implement these strategies? And what stakeholders like government have to play a role in securing a country as a whole?
Yeah. So question was around DNS servers. And what can small businesses do for protection when they don't have a lot of the resources and that? Outsourcing for some of it. So like I showed with the Quad 9 for DNS blocking, you can run your own DNS blocking on your own DNS servers, but I don't want to run my own DNS servers. It's a popular thing in the home lab community to run a Raspberry Pi with DNS blocking. It's called Pi hole, because you want a black hole the address, so Pi hole. Anyways, so very common for that. I don't want to run my own DNS servers at home, because then I have to run redundant servers, because if there's one failure, everything in my home fail. I don't want to deal with any of that. I used to run my own mail server and my own spam filtering. I don't want to do that anymore. That was years ago as well. So finding services that you can outsource it, not necessarily the high cost ones, but things like Quad 9 that you can use, you can get some benefit for that. The other one is, of course, awareness, letting people know what exists. It surprises me every time I talk about Shodan and people haven't heard of it, and they're like, wow, that's scary. It's like, yeah, that's been out for like 10 years. Think of all the good and bad that has happened from that over the time. but there's always so many new things being created. So, getting a bit of advice, if you're talking Australian specific, of course, there's government that has a lot of published advice. Look for published advice from agencies or organizations like CERT teams, computer emergency response teams, or computer security incident response teams. In Australia, the national one is run by the government. They put out advice for every layer, from home users to small to medium organizations, large organizations, critical infrastructure. It's a sliding scale on the amount of advice, because critical infrastructure is going to have a lot more resources than mom and pop at home that need to protect their home devices. But it's also a careful balance. A lot of governments don't want to recommend a business or a particular service because they're seen as, supporting that. Whereas me as an individual, I can say Quad 9, go for Quad 9. There's other ones out there, but my personal favorite is Quad 9. But for a government to come out and say use Quad 9 might not happen, because it's still a separate business entity. So yeah, it's tricky. And a lot of what's going to be needed is more secure by default. And that might be through the internet service providers. If internet service providers, a lot of them say, we don't want to filter the traffic, we don't want to touch it in the middle. But wouldn't it be cool if they did, or if they offered the service and promoted it and, tick a box? But commercial entities, a lot of them that I've seen, they want to charge money for that. So again, people are like, oh, I don't want to pay more money for this. My internet works fine without it. But yeah, and it's letting people know what can happen and what are the easy ways for protection. But the home users is hard. That's why you start small, talk to your family, see what you can do with your friends and family, and sort of get it out through there. But yeah, it's difficult.
And just to follow up on that one, like in Australia, we don't have DNS mandatory.
Yes, yeah.
So, why is that? Why can't we just make it mandatory for
Yeah.
everyone?
So question was around DNSSEC and why it's not mandatory in some countries.
Everyone.
Yeah.
Why don't we mandate it? Like,
The tricky thing, as much as I go on, especially in the last presentation about, you should do DNSSEC, it really only helps in a limited number. It's not zero, but it's a limited number of attack situations, because DNSSEC is integrity of DNS, where you're stopping it from being modified along the way. So you have to be protecting against somebody who's in the middle making those changes. We don't see that commercially in Australia very much. The US does. A lot of their internet providers will actually hijack some domains, or if you do a typo on a domain, they will hijack and send it off somewhere else, and that would show up in DNSSEC. That would be blocked. But yeah, it's tricky to set up. It's very easy to break your entire domain. So the risk reward is not like this. It's like this. If you don't do it right, you can block your entire domain name. And that scares people, as it should, because normally you don't have the thing of one wrong command shutting down your entire network. So yeah, it's network engineers do things purposefully to prevent one wrong command shutting down an entire network. DNSSEC could do that. And DNSSEC then requires all the way up to the top level domain to be signed in order to come down. So .au has to be signed and then on the way through, which I think it is, but not every country is. And if your top level isn't signed, then you can't sign yours underneath it. But then if your top level makes a mistake, your entire everything underneath it goes away. And that has happened. Some of the Pacific Islands have had that problem over the past 4 or 5 years as well. So DNSSEC, yeah. Quad 9, I've never heard, it could happen, but I've never heard of a false positive. Whereas DNSSEC is more balanced out. And yeah, that's the thing for a lot of security, is that you have to remember that a lot of the things may have unintended consequences, or may have problems in the modification of it along the way. And you have to be prepared for how to handle that technically, and procedurally with people as well. Okay. Any other questions? Any from this side of the room? I'm not ignoring you on this side of the room. I'm just not seeing hands up. Any questions on anything that we've gone through for the sessions today? Excellent. I'll close it off there. I'll say thank you to everybody who's been joining over Zoom remotely and anybody who's watching this as a recording after the fact. Again, these slides are going to go up onto the APAN 60 program. Yeah, so please see that. My contact details, I think, are in the program, but you can find me on LinkedIn. It's probably the easiest way to get in touch if you have any other questions afterwards. I will be here at the meeting tomorrow, Tuesday, and Wednesday, but I do have to go home a bit early on late Wednesday night. But I'll be here for the social tomorrow night, and we also have security working group meetings on the Wednesday as well. So hopefully I'll see you around through a bit of the next couple of days. Thanks everyone for coming to this session. Hopefully you found something new. And if it is a lot of information and you think of questions later, do reach out. I'm happy to answer questions after the fact and go on further discussions. Thanks everyone.